So the new topic is, well, what we're getting into is two-dimensional particle kinematics. Particle means that we're not dealing with the orientation of objects. Kinematics means we're not dealing with the causes, we're just dealing with position, velocity, and acceleration. 2D, so we were doing it along a line up until now, but 2D means that these things can now move in a plane. So they have more ability to move. But before we can get to this, before we can apply it to actual 2D particle kinematics, we need vectors. And so before I get into actually applying this to kinematics, I have to describe the math of vectors. Okay, so remember that for one-dimensional particle kinematics, directional quantities, so quantities that have direction associated with them, quantities, and the directional quantities that we were dealing with were position, displacement somewhat, although we didn't use that very often, velocity, and acceleration. Sorry, leave off these vector things for now. So position, displacement, velocity, and acceleration. These were given by signed numbers. The plus or the minus indicated the direction. Remember, though, I mentioned this a couple times. It wasn't a big focus, but so these directional quantities could have always been given as a magnitude and an arrow. Okay, so for example, if we have a problem where something starts at a height of, 0.5 meters, and it's launched up into the air and then comes back down, we choose a 0 position and a positive direction. Okay, and based on those choices, and this thing is in free fall, what's the acceleration of this object? That's right. So the acceleration would be negative g, that's perfect, or negative 9.81 meters per second squared. Okay. but that's always equivalent to, so that's the same thing as saying down with a magnitude of 9.81 meters per second squared, right? That sign could have been indicated as an arrow direction. Okay, it's just that the arrow direction for motion along a line only has two possibilities. So this arrow only has two possible directions. Well, that's the idea of a vector, except that now if we go to 2 dimensions, and the same idea works in 3 dimensions too. Now in 2D, an object's possible direction let's see, that's not good. An object's possible direction has more than 2 choices. Okay, so in 1D, or motion along a line, if you have an object here, it can only go this way or that way, right? In 2D, you have an object here. It can go this way or that way, or any of the other infinitely many directions in the plane, right? So in 1D, there are 2 choices. In 2D, there are infinitely many choices. So representing the direction by a positive or a negative isn't going to work anymore. So direction can't be represented by plus or minus. It can still be represented by an arrow, though, and that's what we're going to do. Okay, so that brings us up to the definition of a vector. And a vector is a mathematical quantity with 2 properties. Or instead of quantity, let's say a mathematical object. So what's a mathematical object? Like, so a table is not a mathematical object, but a triangle or something is, okay? It's not something that's there in the real world, but it's a mathematical thing. You can imagine it. And this one has 2 properties. And these you need to remember. The first one is a magnitude. And the second one is a direction. You can think of that as an arrow whose magnitude is given by the arrow length. Okay, so for example, you can think of that as a vector, and if you measure it, the length of that vector tells you the magnitude of that mathematical object, and the direction is, the direction that it's pointing. By the way, two directions that'll come up every once in a while. So if we're dealing with stuff in 2 dimensions, then you can draw everything in the plane, right? But in 3 dimensions, you can't draw every vector. So a lot of times it's useful to have a representation for vectors that are coming out of the page or going into the page. So here's what people use. A circle with a dot in the middle is a vector coming out of the page. It's like you're looking at the tip of an arrow is the idea. And a vector going into the page is a circle with an X through it, like you're looking at the feathers of the arrow. One thing to keep in mind, so I said these are important. These are going to show up on a quiz at some point. But something else that's important to remember is that neither of those 2 properties is a location, okay? So a vector does not have a location. And so when we do calculations with vectors, we're going to imagine moving them around from this point to this point, because you can move them around and it doesn't change the value. The only thing that a vector contains is a direction and a magnitude. Okay. And before we talk about how we're going to do calculations, we have to talk about some sort of graphical, physical meanings of vector calculations. So I'll call this the physical meaning. And we're going to do 2 calculations. We're going to add 2 vectors. And we're going to multiply a vector by a number. And a number, another way to thing you hear numbers called is a scalar. So a scalar is, I mean, it's just a fancy word for a number. Not that fancy even. But so we're not multiplying 2 vectors together. We're multiplying a single vector by a number. Okay, so the first one is adding vectors. So the idea is you use the 2 vectors, let's say 2, or it works for more vectors too. To create a path from a start point to a finish point, or to an end point. Then once you've done that, then the sum of the vectors which is called the resultant, is just the shortcut from the start point to the end point. Okay, so here's an example of this. So let's say that we have this vector and we want to add it to this vector. Okay, how are we going to do that? Okay, so I'm going to choose some starting point. It doesn't matter where because vectors don't have location. And I'm going to start at that starting point, take one of those vectors as the first leg of this trip. Then where that one ends, I'm going to put the second one. Okay. So this is the start point. This is the end point. And so the resultant vector is just the shortcut from the start to the end. Okay. What if I did them in the other order? Because you know when you add numbers, what? You come back here. When you add numbers, the order of operations doesn't matter. 3 plus 2 is 2 plus 3. So let's say that instead this is the start point. Okay. And then that takes us a little bit lower, and then from there we take this leg of the journey. So here's the end. And if you do it carefully, because location doesn't matter, this vector and this vector are the same. Okay. So the order of operations doesn't matter. And so now we're going to represent position, velocity, displacement, and acceleration as vectors. And what that means is if you have a case where you're adding two accelerations, okay, like we saw an example of that would have been in the relative motion equations that we did in the last couple of classes. If you have to add two accelerations, and one is this way, and one is this way, you add them using the vector rules, and the sum of those two vectors follows this physical meaning, okay? And if you did it carefully with angles and rulers and stuff, you could do this all just in terms of angles and stuff, okay? That's not how we're going to do calculations, but that's what it means. It kind of doesn't have an answer. So any more than like, what are the units of a triangle or the units of a number, okay? Those are mathematical objects. The units come from whatever you're using this mathematical object to represent. So in the example that I just gave, where say these are accelerations, then these vectors would have units of meters per second squared. If you're doing it to add two positions, then they'd have units of meters and so on. Okay, so the vectors themselves don't have units any more than like a number has units on its own. Okay, so now what about multiplying a vector by a scalar? Well, multiplying a vector by any number, you can do it in two steps. So we're going to think of first what it means to multiply a vector by a positive number. And then after that, we're going to think about what it means to multiply a vector by -1. And with those two steps, you can multiply by any positive number, any negative number. Okay, so first, to multiply a vector by a positive number, keep the direction the same. And multiply the magnitude by the number, or the length of the vector by that number. So, for example, if we wanted to multiply 3 times this vector, no, we could do it like this. Don't worry, it's worth it. Damn it. Ah! Okay, so there's 1, 2, 3, 3. And so the resultant vector is just this. Okay, keeps the same direction. The length changes by 3. Can you make vectors shorter by multiplying by a number? Yeah, the number just has to be less than 1. Okay, so what if you're multiplying by a negative number? Well, just think of going in order. First multiply by the positive number and then multiply by the negative 1. So to multiply a vector by negative 1, negative, keep the length the same, and switch the head and the tail. So negative 1 times this vector is that. Okay, so to multiply a vector by negative 17.5, you make the vector 17.5 times as long, and then just move the head to the other side. This is a way that you could do all, with fine graph paper, and a straight edge, a ruler. You could do all your vector calculations this way. But we're not going to. We have an easier way. Using vector components.